Up next, we will hear from one of our amazing graduate students, Jonathan, if you want to come up to the stage. Jonathan is a PhD student in mechanical engineering with research interest in dynamic control of robots for synergistic human collaboration. His doctoral research is focused on developing an interactive framework for developing artificial intelligence for minimally invasive robotic surgery.
My name is Jonathan Madera. I'm a PhD student in the Human-Enabled Robotic Technology Laboratory, and so this is going to be just a short presentation, short overview of my research. And so it's really centered around robot-assisted laparoscopy. You see if this video plays. Yes. And so what's going on in this video, sorry if you're a little bit squeamish, I should have mentioned that before. You see multiple kind of surgical manipulators working together to kind of do this surgery. And so there's literally no AI in here. It's just a human sitting and telemanipulating at the robotic console, and then they have their surgical assistant kind of next to them. But essentially, this video here kind of displays the intelligence that I hope to build with my research. And so obviously, this is kind of like an AI computation conference. So really like the big question is, how would we build this system? Really, the main question is kind of what are the essential components for creative collaborative teams and behaviors, and really kind of boils down to two questions: what makes a good team and what makes a good team member? So kind of just jumping right into it in terms of principles for understanding teams and what makes a good team. Really, teams consist of constituent members and their member abilities, how those members interact, and how and what information is communicated. So kind of moving along, because time's running low already, basically, is that we have kind of what makes a good elements of a good collaborative agent or a good team member is really like four different things. So you have sort of this decision maker that kind of establishes what the task actions are, what the output communication is. Then you have some sort of data acquisition, data flowing into the robotic system, some sort of information processing, which can essentially store long-term or short-term memory, and hopefully all of this makes sense when I kind of see how we apply it. And then the last thing here is that the decision maker can also inform how our information is processed, and so it's kind of like a really nice loop in this sense. So in terms of how do we actually get the robotic system to move, we kind of start, that's kind of like the first aim. It really starts from kind of like this learning skills from demonstration pipeline, where instead of actually just collecting a bunch of data, we do kind of like an online interactive sort of thing where as the surgeon's manipulating, they have this communication framework which allows them to kind of annotate the data online, segment the skills, pre-process those skills, and then learn those skills as what I like to call, or what I call Gaussian mixture models, which are essentially just probability distributions along the data, which allows us to basically ask the question, what should the robot do given the human's in some spot, and also like what the human should do. So again, that kind of breaks down to these two questions, really trying to figure out how should I move if you're the robot, and then what the human needs to know is like some sort of communication in terms of how will the robot move and how does the robot believe that I should move, right, when we're kind of working in tandem. And so in order to kind of answer the questions on the right, in terms of feedback to the human, what we do is we kind of take one of these skill models and we project those trajectories as visual feedback back onto the robot's vision. And then the second thing that we do is we kind of think of the robot trajectory as kind of like an attractor, and it kind of pulls and pushes on how the human user is manipulating. And so that kind of gives you a sense of proprioception of what the robot should do. And I think I may have messed this up, yeah. Oops. The second thing, and there's actually two images here, apologize for this, is really asking the question, how should I move? And so the big thing that was recently published is essentially making sure that if the human makes a wrong movement that isn't aligned with how the original task was computed, we can actually still update the robot. So I'll show you kind of like two videos of this working for a knot tie. On the left is kind of like a successful collaboration attempt, and these are exactly the same trajectories. And so really, spoiler alert is that it sometimes works and it sometimes doesn't, mostly because it's the problem with learning from demonstration in the first place. And so the idea here is that surgical skills, most robot manipulation skills are not actually just trajectories that you blindly follow with some sort of synchronization. They're a lot more than that. And so another recent paper kind of updates this pipeline to, kind of generalize these skills and think of skills now instead of just kind of some learned trajectory, but also some combination of sensory information that kind of allows us to adapt the surgical skills in so that we can generalize them. This is kind of like the very first start of the framework. There's two more aims related to kind of, so this is like the low level processing. How does the motion actually happen? This needs a lot more, I guess, a lot more time to get to the second point where we talk about high level planning, meaning how do we actually get skills from the library, plan with a human user operator kind of in an interactive framework so that you can do all of the things together. And then really the last point of this in terms of the sort of the thesis direction is to personalize this, knowing that collaboration, the way that you collaborate with one person might be different than another. So that's basically it. Thank you. Wow.
Thank you so much, Jonathan. Up next, we have Armand. He is a second-year PhD student in electrical and computer engineering whose research focuses on the intersection of brain-computer interfaces and medical robotics. He received his bachelor's in mechanical engineering from the University of Massachusetts Amherst and his master's in robotics and control systems from Columbia University, where he specialized in rehabilitation robotics. Please join me, everyone, in welcoming Armand.
There we go. All right. Hey, everyone. My name is Armand, and I'm a researcher in the Clinical Neuroprosthetics Brain Interaction Laboratory. And today I'll be talking to you guys about brain-computer interface control of assistive robotics for ALS. So the high-level motivation for this work, right, is that millions of people live with motor impairments. Now, in the case of ALS specifically, there are about 30,000 cases at any given time in the United States. And so in a condition like ALS, what will happen is that people will remain mentally present and mentally sharp while this neurodegenerative process progresses. And so this will lead to full paralysis over time. And so as you can imagine, as this is happening, this is a huge, tremendous impact on their quality of life. And so the long-term goal of research like this is to enable individuals with this severe paralysis to control assistive equipment that will help with day-to-day tasks. In this particular case, we're looking at equipment that is based on neural intention alone, okay? And so one of the classical problems in non-invasive brain-computer interfaces is that these BCIs will typically require a session-specific calibration. And so calibration can often be somewhat time-consuming, and it limits the practicality in a clinical sense of the system itself. As you can imagine, if someone has a condition like this, they don't want to recalibrate the system every hour or twice a day or whatever it might be. So there's been a lot of work going into how can we get around that and how can we avoid doing a calibration, right? And so that's where the transfer learning approach really comes in. And so the high-level basis for the transfer learning approach is that we collect data on healthy individuals, in a different time and place, and through a machine learning approach, we've found a way to apply that model to new individuals coming in. Now, the research question here is really, can you actually transfer this model from healthy individuals, right, people who, you can collect a ton of data on, and can people who have a condition like ALS actually use these models, even though their neurophysiology may be a little different? And so that's the research question there. And so the architecture of the system that we're using to test this, right, is basically what you see here. So at the center of it, there is a control computer, okay? And this control computer really does two things. Number one, it is running a task that is going to prompt the user to do one of two things. And one of them would be to envision yourself reaching for an object just mentally, right? So that's called motor imagery. The other one would be to remain at rest. Now, once the participant has been prompted, that's when a real-time loop is going to be running, processing the EEG data and making a decision based on the data that it's seeing coming in. And so that's what you can see on the left, which is the EEG data that streams in. Now, during that neuromodulation process, there will be two types of feedback. One is the visual feedback that is coming in from the screen that is actually prompting you. The second is a stimulation device that you see in the bottom right corner there. And that stimulation device provides sensory stimulation on the actual muscle in question. So if it's a right arm task, we're going to be stimulating the right arm, of course. So if the algorithm is able to amass enough confidence in a short enough window of time, then it will move the upper body exoskeleton robot that you see in the upper right-hand side of the screen there. And that's actually, by the way, the Harmony robot, which was developed initially here at the Renew lab at UT. And so basically, we have been doing this study. It's ongoing. We're now working with, I believe, our 5th individual. And so I'm only showing the first one of the subject's results here. But in this particular subject, we were able to achieve 89% decision accuracy, which is a promising start. Now, what this means is that in the cases where a decision was able to be made, it was the correct decision in 89% of the time. And in this individual's case, we had over 500 trials over a 5-week period. And so there's really two parts to the analysis. There's the system performance, which I just mentioned, and then there's the kind of the neural results, right? So we want to do an analysis to ensure that the data coming in actually makes sense and is consistent with people doing a similar task in terms of like a healthy population. And indeed, what we're able to see is that, and on the bottom right-hand side, is an average of all of the motor imagery tasks. And you can see each of those lines is one session, so there's 5 sessions. And you see a modulation on the motor imagery class that is very consistent with how people who are healthy have the same modulation. And on the other side, you see the rest, so that's on the bottom left-hand side there. And you can see that there is no such modulation in that case. The line is centered mostly around 0. So this basically helps demonstrate, of course it's only one subject and we're still doing the study, but it helps demonstrate the effectiveness of this transfer learning approach. So I think that's probably time, so thank you for listening.
Thank you so much, Armand. Up next, we will have Arpit. He is a 3rd-year PhD student in computer science and a member of the Robot Interactive Intelligence Lab. His research focuses on developing general-purpose deployable robots for real-world environments, with an emphasis on failure-aware and safe robot learning to enable reliable autonomy in the wild. Please join me in welcoming Arpit.
My name is Arpit, and I'm going to present my research towards safe household robots via simulation-driven learning. So the main problem is training and evaluating robots for safety in the physical world is really dangerous, as you can see here. So simulation, as you can think, is a much safer alternative for this. And so in this talk, I'm going to talk about 2 problems that we use simulation for. So first, how can robots leverage simulation for learning directly, safely in the real world? And second, how can we leverage simulation to benchmark safety of household robots? So let's talk about the first one. Now, imagine you have a robot at home. You would want to teach the robot directly some skills, right? Directly showing it to them. So for instance, here, making a coffee. However, you want the robot to learn that skill in a safe and reliable manner. You don't want this kind of a situation. So in this work, Safe Mimic, we study how robots can learn these multi-step mobile manipulation tasks from a single human video, but most importantly, safely and autonomously. So on a high level, Safe Mimic has 3 modules. The first one parses this human video to obtain some kind of initial action, initial action trajectory, which usually fails. So we have the safe and autonomous adaptation of this action trajectory. And then the third one, the robot learns from this new action that it just found out. So in this talk, let's just focus on the safe and autonomous adaptation. So let me explain this through this video. So what happens is the robot, the task here is to place the pot in the sink. And the robot gets this initial action from human of how to move this pot. However, this usually fails. So what it needs to do is refine this action. So what it does is it tries these different sampled actions and sees whether this is safe or unsafe to execute. And how it does that, I'll talk about it in a few seconds. Now, the cool part is whenever it thinks that there's no safe action possible, it just simply unwinds and then tries a different action. And this makes this process autonomous, which is really important because you don't want to keep interrupting the robot. And it does this process until it succeeds. So at the core of this, which I mentioned, was evaluating whether this action is safe or unsafe. And this is what is learned in simulation. And you want to learn this in simulation because you need data of unsafe behaviors, and you can't really get that in real world. So on a high level, we learn these safety queue functions. And it is basically one, if the current or the next state is unsafe, which is evaluated in simulation. And for example, in here, it's the robot is trying to place a pot in a sink. It's safe until it collides and exerts too much force. And we train this in a lot of different ensembles of environments in simulation. So how do we check whether this method is effective or not? So we have these 7 multi-step complex mobile manipulation tasks, and we evaluate our method on this. So as you can see over here, there are a lot of videos, but what I'm trying to show here is that the robot is trying to learn these new skills just by watching a human and trying it out in the real world. And the way it is we are able to rely on the robot to try it out in the real world is because we learn these safety functions in simulation. And the cool part is that you could argue that you can directly learn these skills in simulation, but the thing is that transferring these skills directly from sim to real is much harder than actually learning these safety queue functions, which is kind of like an easier problem. So this transfers much better. So this was Safe Mimic. Now the second question which I was talking about is how do we evaluate for safety? Now the thing is, if you use simulation to evaluate for safety, this is what's going to happen. So in that same situation, there's no realization that there's an unsafe behavior that happened. So most simulators don't have this. So what we did was, can we develop a system or a framework which can detect whenever there's a damage happen? So as you can see here, the laptop gets damaged, the glass gets damaged, and we provide this unified, and this is like a simulator and task agnostic safety signal. So on a high level, we call this oopsieverse. On a high level, oopsieverse consists of 2 modules. One is called damage sim, which is basically a simulator agnostic plugin you can think. And what it outputs is these damage indicators, and we model these different kind of damages like impact, thermal, fluid, tension, etc. And the second is a oopsie bench, is what we call, which is basically a benchmark where future works can evaluate whether how safe, unsafe their policies are. So how can we use this? Let me give you one example. So in this task, the robot needs to place this cereal box in the shelf, but it needs to do so by pushing certain objects, but it shouldn't push like fragile objects like wine glass. And what happens here is this is an example of how the damage indicator from oopsieverse can be used for reinforcement learning. So what you see here on the green curve shows the task reward, and the orange curve or yellow curve shows the damage reward. And you can see that as the training progresses, because of the indicator from damage sim, the task reward is maintained, but the safety reward is reduced. And yeah, so in summary, these are 2 different ways that simulations can be leveraged to improve the safety of household robots. Thank you.
Thank you so much, Arpit. Up next, we have Ana. Ana is a 3rd-year PhD candidate in neuroscience working under the mentorship of Dr. Jose del R. Milan in the Clinical Neuroprosthetics and Brain Interaction Lab. Her research focuses on the design and implementation of brain-computer interfaces that decode neural signals in real time and translate them into actionable control commands for computers and robotic systems. She aims to create clinically impactful neurotechnology for individuals with motor and cognitive impairments. Please join me in welcoming Ana.
Hi, everyone. So the topic of my talk today is training autonomous robots with implicit human feedback, combining brain error-related potentials with tamer. So y'all are probably thinking, what the hell does that mean? Basically, what we're trying to do is we're creating a system that can allow users to train robots by simply observing them make mistakes. And there are two components that are involved to make this possible. One of them is the reinforcement learning algorithm that we're using. It's called Tamer. It was developed here at UT by Dr. Peter Stone and Dr. Brett Knox. And the way this works is instead of having a hard-coded reward function, the agent learns directly from human feedback. And in practice, a human observes a robot do something and presses buttons for positive and negative feedback. And we use that to build a model of human preferences that is then adjusting the policy. So this is great, but this is creating a few problems from the human experience perspective. One of them is that pressing those buttons increases the cognitive and physical load. So you have to hold the controller, you have to explicitly provide feedback by pressing buttons, and it creates an unnatural interaction. But more importantly, this is not possible for individuals who could benefit from an assistive device the most, which are people with motor impairments. So we're solving this problem by integrating Tamer with a brain-computer interface, where we are reading out brain signals from the user, and we're using machine learning techniques to decode intentions or perceptions from the user, for example, perceptions of errors, so you probably can guess where this is going, and that information is passed directly to the robotic system as a command. So in this case, all the user has to do is just watch the robot perform, and everything else is happening in the background. The feedback is implicit, error perception happens naturally, and everybody doesn't require extra cognitive effort. And it's accessible to all, including people with motor impairments. So how are we recording those brain signals? We are using EEG, where you place electrodes on the top of the person's head. And those electrodes are picking up amplitude modulations that are produced by brain cells, large populations of brain cells in response to some stimuli in the environment. And lucky for us, humans produce a very strong signals whenever they perceive errors in their environments or mistakes. And it looks like this. It's called error-related potential. It's shown here in red. And for comparison, I'm showing in green the resting neutral brain state. So this creates a binary classification problem where you're trying to discriminate between the presence of an error-related potential or negative feedback that you could provide to a robot versus the resting brain state or no feedback. So after a few signal processing and feature engineering steps that I have no time to cover, this is the performance of our brain decoder. It's pretty good. The area and the precision recall curve is well above chance. Our TPR is 64% and TNR is 84%. So we tested this system on this robotaxi task where the agent is this yellow taxi moving around in a grid world, and it gets points for picking up humans and it loses points for hitting cars. But once again, the tamer, the algorithm, has no idea about those environmental rewards. All it gets is the punishment from the user. And we had 4 subjects who completed 2 phases of the study. The first phase was a control phase where they were pressing buttons like anybody would do with tamer usually, and we used this data to build individual brain model, brain decoder model, and then in phase 2, we used this model to decode those signals in real time, provide the feedback to tamer, and all the subject has to do is just watch the robot. So now the question is, how does manual feedback compare to BCI feedback? So this is what I'm showing here. On the x-axis, I have the number of steps that the taxi took. And on the y-axis, I have the number of points that it was able to get. And I'm comparing random policy, which is the dashed line there, manual feedback in orange, and BCI feedback in blue. And you can see 2 exciting findings here. The BCI feedback is outperforming random policy, and with a few more steps, it can reach the same level of reward as manual feedback. And those steps are only about 2 more minutes of training. So next, we want to test the system on a new task. We want to test this in a real-world robotic training. And most importantly, we want to test this with people with actual motor impairments. And I want to thank my PI, Dr. Jose Millan, and our collaborators, and also you guys for listening to my talk. Thank you.
Thank you so much, Anna. Last but not least, we have Nathan. Dr. Nathan Tsao is a postdoctoral fellow with Texas Robotics, advised by Joydeep Biswas and Peter Stone. His research bridges the gap between robotic efficiency and human social values, focusing on how mobile robots can complete tasks reliably while interacting naturally with people. Nathan holds a PhD in computer science from Yale University and brings a mix of academic and industry experience, having previously worked as a research engineer at the Stanford AI Lab and a senior software engineer at Sequoia Capital. Please join me in welcoming Nathan.
Thank you, April, and thank you all for staying. I know I'm the last thing holding you guys here before tours, so I'll make this quick and hopefully engaging. I love the idea of learning from implicit feedback, so great last talk. I'm going to tie that in. Actually, it's very similar to what I'm going to talk about here. I work in human-robot interaction, and today I want to show you a little bit about our work. I don't know, this video doesn't have any audio, but here you can see one of our navigation robots moving in Anhis Gymnasium, which you may go tour next. And you can see here that it's moving through the environment. There are no people around. I also teach an FRI stream, and one of the first questions I like to ask in this class is, what defines a robot? What capabilities are required? Can I get some audience input here, actually? Does anyone know what capabilities might define a robot? You can just shout it out. Autonomy, okay, good. There's, within autonomy, other components that I'm thinking. Perception, okay. Memory, there might be memory. Processing, yep. Okay, great. Yeah. Movement, okay, great. Yeah, I think we captured a lot of the things. So we have an environment, we have the world typically, and then we sense in that. So we might have something like a LiDAR or a camera where we read information about the world, and based on that information, we form a plan. So here we have a plan represented by this neural network, and from that plan, we then take actions in the physical world like you guys are talking about. And I want to show this little example of this process going on right here. Let's see if this plays. There should be audio. Can you guys hear it?
Here, watch this.
Okay, there.
Oh my God, it's heavy. Oh. Thank you. Have a nice day. He said thank you. Holy. Oh my God, is this what you're doing? Huh. Oh my God. Huh. Watch this. Here we go. Buddy, here you go. Oh, you ungrateful.
Okay, interesting interaction here. These delivery robots are trying to deliver something to someone somewhere, and this other person has stopped, seen that the robots were stuck, and helped them. And there was a breakdown because the first robot replied after getting help, thank you, and then she had this expectation, and when the second robot didn't say say thank you for helping, there was a problem. The expectation was broken. So what's going on under the hood? I won't go into detail, but we execute these various components within the Sense, Plan, Act framework. And typically, we only really care about task execution, that is getting the robot to deliver its object to whoever is getting the food or whatever is in this robot. We don't typically think about other people who might interact with that robot, or really the human-robot interaction component. And I would argue that this is really a value alignment problem, which I'll define in this way. We have some true underlying objectives, say getting the food to the location it needs to get to, and then we have a specified objective in the system, and a system that fulfills that true underlying objective succeeds a value alignment. The problem is we don't typically capture everything that we need to capture in the specified objective, because it's very hard to know what the true objective is. The thing that was missing in our delivery example was accounting for that person that actually helped the robot and their expectations. So the way that we would typically design a system would look something like this for the delivery robot, let's say, where we have an agent, the robot, we have an environment, and then we have a designer that exists outside of that setup. And information flows from the designer into our system that we develop, and the designer and the engineers and everyone involved builds this system. They look at its behavior, they find these problems, and they go correct them. But inherently, information is only flowing one direction, from the person into the system. And this works fine. These are some examples of works that I've done similar to this to achieve value alignment, where we design specific reward functions or losses to do specific tasks. However, what we really want is we want the human to be a core part of the system. And what we've done is we've pulled this human into the system itself. And now what we can do is we make the assumption that agent actions in the world will influence humans, which are now part of the system. And when the agent takes actions, it doesn't just influence the external state of the human, but it influences the human's internal values. These are things like trust, expectations. And when this occurs, what we can do is we can actually optimize for that. You can see down here in the reward, our satisfaction is the component of the reward that actually optimizes for that human internal state. And the way that we actually get an estimate of that internal state is via this observation function. So this framework should allow us to incorporate humans into this learning process and adapt to them in real time so that we can repair things like when expectations break down. I think I'm out of time, so I'll end it there. Thank you, guys.
Thank you so much, Nathan. Thank you to all of our speakers. Let's give everyone one last round of applause.